Hey everybody, thanks for showing up to this video too. This is the second of a couple of videos on probability area models. And in this one, we're going to deal with the question of the probability of A or B, which is called a union of events, by the way. Anyway, let's summarize a little bit what the first video showed us just to be complete here. That we learned in that video that the probability of an event is always some positive number less than or equal to 1. We also learned that area models can be used to kind of visualize and calculate probabilities of a combination of events. All right. We also learned that when we have the probability of A and B, the probability of two events happening at the same time, all we have to do is multiply the probability of A times the probability of B in the same way that we multiply the base times the height of a rectangle to find its area. That's why we use the area models. By the way, that probability of A and B is called an intersection of events, the intersection of A and B. And in this video, we are going to deal with the question of the probability of A or B, which is called the union of A and B. Now, probability area models can be used for both kinds of questions here, and we have to be very observant to make sure that we notice whether or not we're talking about an or an and kind of situation, because the calculations are different. All right, so I'm going to set up a problem here for you to demonstrate this. Ruby and Fred are joining forces to cover up some graffiti on a neighborhood wall. Each will choose a color of paint to bring, randomly chosen from all the half-empty cans of paint from their garages. Based on their supplies, Ruby has a 30% chance of bringing blue paint and a 70% chance of bringing white paint. Fred has a 25% chance of bringing yellow paint and a 75% chance of bringing green paint. All right, so that's a lot of information. Let's see if we can kind of simplify it down here into an area model. Ruby on one side of the square and Fred on the other, and then we'll add their probabilities. Blue and white for Ruby and yellow and green for Fred, and there's the numbers. All right, so all we have to do now to complete this area model is to multiply our probabilities together. And 30% times 25% is 7.5%, and etc. It's very easy to use a calculator to come up with the probabilities there inside our area model. And as we saw in the last video, each one of these numbers represents an and situation. For example, the probability of blue and green paint showing up at this graffiti removal project is 22.5%. The probability of blue and yellow is 7.5%, and the probability of green and white is 52.5%, etc. So all of the numbers inside each cell of this area model represent an and kind of situation, which, as we're now saying, is called an intersection of events. All right, but what if my question was something like this? What is the probability that at this graffiti removal project we have either blue or green paint? I'll take either one of them, either one. So if you think about that, Ruby has a 30% chance of bringing blue paint, and it doesn't matter what kind of paint Fred brings. There's 30% chance that blue will show up at this graffiti removal project. At the same time, there's a 75% chance that green paint will show up. So 30% for blue and 75% for green. All we're going to do is actually, and this may surprise you, but when you see the word or, we're going to add these probabilities together. So we're going to add 30% plus 75%. But you know what? That makes over 100%. And as we saw, probability is a number less than or equal to 100%. So this cannot be the final calculation. And it wouldn't make sense anyway. So, but what we are noticing, hopefully, that you notice that both of those events, blue paint from Ruby and green paint from Fred, overlap at that 22.5% corner there. All right. And in fact, that 22.5% is a part of the 30%, and it's also a part of the 75%. So it's been added twice when we add up 30% plus 75%. All right. So you may have to want to repeat that on the video, because I know it gets complicated to say all this stuff. But since we've added that 22.5% twice, the proper thing to do is to subtract it once. All right. So what we've done now is we've taken the probability of blue plus the probability of green, and we're subtracting the probability of blue and green. All right, and that's how we'll come up with our probability of blue or green being 82.5%. All right, so it is a little bit more complicated procedure, and it's not very obvious or intuitive, perhaps, just given it, but it does kind of show up in the area model. It demonstrates why we have to do that little subtraction part there, because it's where two things overlap, and we don't want to count the same number twice. Let's try this one more time. What's the probability of white or yellow paint showing up on our graffiti removal project? Well, look at that. White is 70%, yellow is 25%, and then we look at the probability of white and yellow, that's 17.5%. So it's actually pretty quick to come up with our calculation here, 77.5%. Let's summarize a little bit here, okay? A union of events, that's what we've just been talking about here. A union of events, that's a probability of A or B, and we calculate that by taking the probability of A plus the probability of B and then subtracting the probability of A and B, which incidentally, sometimes that's 0. Probability of A and B might be 0, but that's okay. We're still going to subtract it. All right. Whereas like we did in the other video there, what we're now calling an intersection of events, that's the probability of A and B, and that's simply multiplying the probabilities of A times the probability of B, just like finding the area of a rectangle. All right. I'm going to leave you with one more example here, a situation that you may be somewhat familiar with, that is rolling two dice. Let's say you have a red die and a blue die, and you're going to roll those two dice together and add up the numbers. Well, this chart right here shows you all the different possibilities that could happen when you do that. And as you can see, there are 36 different outcomes from rolling two dice and adding up the numbers. Each one of them has the same probability. They are all equally likely. They all have a 1 out of 36 probability of occurring. All right? So this is, in a sense, kind of an area model. It's a little bit different because every cell in the model has the same probability, but we can still use it. It's still very useful, in fact. For example, here's a very simple question. You might not even need this one. What's the probability of rolling a red 2 and a blue 5? Well, that only happens at one place in the chart, right there at 7, and that's a 1 out of 36 chance. Okay? Very easy to calculate. Slightly different is what is the probability of rolling a sum of 7? Because it could be this 2 and the 5, or it could be a 1 and a 6, or it could be a 3 and a 4, or we could reverse the numbers, and we end up actually with 6 different ways that you can get a sum of 7 from rolling two dice, and so that's actually 6 out of 36. We have to add all those together. Even though the word or doesn't show up in that question, it really is kind of it's a union of events, all right? Here's another one. Let's say, what is the probability of rolling the same number on both? That's also a union of events. It could be 1 and 1, or 2 and 2, or 3 and 3, or 4 and 4, etc. And so we add up all of those 1 out of 36 possibilities to come up with 6 out of 36. For rolling doubles, you might say. What about this one? This is a little bit more complicated. What is the probability of rolling a 2 or a 3? Now, it doesn't matter which color dice you roll the 2 or the 3 on. I want to know, what is the probability if I roll two dice that one of them is a 2 or a 3? Well, let's see. Well, you can use this area model here very effectively for this kind of a question. You can see that there's a 12 out of 36 chance of rolling a 2 or a 3 on the red die. And it's the same for rolling the blue die. There's a 12 out of 36 chance of rolling a 2 or a 3 on the blue die. You can also see very quickly now that we have counted 4 numbers twice. So we're going to subtract that 4 out of 36, and then we end up with our answer, 20 out of 36. Pretty cool, huh? Let's do one more. What is the probability of rolling a 6 and a 4? Again, we're not specifying which die gets the 6 or which die gets the 4, just what's the probability of rolling a 6 and a 4? Well, it doesn't seem like that's an or kind of a question, but it really is, because 6 and 4 make 10, and there are 2 different ways to get a 10. So we add those up. There's the 6 on the 4 one way, or the other way. And so we have to add those both together to come up with our final calculation of 2 out of 36. All right, well, this was a little bit longer of a video. We're gonna leave it right there. I hope you enjoyed it. I hope you learned a few things about probability. My final comment to you is, please study and think about probability. It's one of the most important kinds of mathematics that we human beings on Earth have to deal with. Probability guides so many of the events that happen to us in our daily lives. It's a very, very important and practical type of mathematics. It's challenging for sure, but that's because it is so relevant to our daily experience. Okay, thanks again for watching. I hope you're doing well, and I hope to see you soon. Bye-bye.